y equals sin inverse x the whole square is given. Show that 1 minus x square yn plus 2 minus 2n plus 1 x yn plus 1 minus n square yn equals 0, and hence find yn at x equals 0. Y equals sin inverse x the whole square is given. Therefore y1, which is the first derivative of y, is obtained as 2 times sin inverse x into derivative of sin inverse x, which is 1 by root of 1 minus x square. When you multiply both sides using root of 1 minus x square in the numerator, you get the equation y1 into root of 1 minus x square equals 2 times sin inverse x. When you square on both sides of this equation, you get y1 square into 1 minus x square equals 4 times sin inverse x square. But sin inverse x the whole square is y. Thus, RHS of equation 1 can be rewritten as 4y. Now we will differentiate both sides of equation 1 with respect to x. Here we have to make use of product rule for differentiation. Differentiating LHS of equation 1 using product rule, we get 1 minus x square into 2 times y1 into y2, where y2 is the first order derivative of y1 or y2 is the second order derivative of y, plus negative 2x into y1 square. And when we differentiate RHS with respect to x, we get 4 times y1, because derivative of y with respect to x is y1. Number it as equation 2. When you divide equation 2 by 2y1 throughout, you get the equation 1 minus x square into y2 minus xy1 equals 2. When you bring 2 to LHS, this equation can be rewritten in this format and call it as equation 3. We are asked to prove this result, and yn is the nth order derivative of y. By Leibnitz rule, we have dn of uv equals unv plus nc1 un minus 1v1 plus nc2 un minus 2v2 plus etc., where un is the nth order derivative of function u. In equation 3, when we apply Leibniz rule, we have to select y2 as u for this term and y1 as u for this term, because we are expecting terms yn plus 2 to appear, also yn plus 1 to appear for the result to be proved. When y2 is selected as u after application of Leibniz rule, you will get the nth order derivative as yn plus 2. When y1 is selected as u, you will get the nth order derivative as yn plus 1 after application of Leibniz rule. And that is the reason why we select u equals y2 and u equals y1. When you apply Leibniz rule for this term, after application of the rule, you get the term 1 minus x square yn plus 2 plus n into negative 2x yn plus 1 plus n into n minus 1 upon 2 into negative 2 into yn. When you apply Leibniz rule to this term xy1, treating v equals x and u equals y1, you get x yn plus 1 plus n into 1 into yn. Notice that minus 2x is the derivative of 1 minus x square, minus 2 is the derivative of minus 2x, and we can no longer differentiate minus 2 because it will give us only 0. That's why we have stopped application of Leibniz rule for this term with only 3 terms. Similarly, we have derivative of x is 1, and we will be getting 0 as the answer when you differentiate 1. That's why we have stopped application of Leibniz rule to this term with only 2 terms. After simplification, we obtain the desired result to be proved. Call it as equation 4. In equation 4, when you give x equals 0, this term becomes 0 and you are left out with 1 minus 0 into yn plus 2 minus n square yn equals 0, which can be written as yn plus 2 equals n square yn. At x equals 0, we have the notation yn plus 2 at x equals 0 equals n square times yn at x equals 0. At x equals 0, we have y1 equals 2 times sin inverse x upon root of 1 minus x square. Giving x equals 0, we get y1 equals 0. We can find out y2 by taking derivative of y1 with respect to x, that is d by dx of 2 times sin inverse x upon root of 1 minus x square. Here we apply quotient rule and we get y2 equals 2 times 1 minus sin inverse x upon 2 into 1 minus x square the whole raised to 1 by 2 upon 1 minus x square. Here when you give x equals 0, you get y2 at x equals 0 is obtained as 2. Following similar steps, you can verify that y3, y5, y7 etc. are all 0 and y2, y4, y6 etc. at x equals 0 are non-zero. We can generalize yn at x equals 0 for odd values of n equals 1, 3, 5, 7 is 0, and yn at x equals 0 for even values of n equals 2, 4, 6 etc. is obtained as 2 into 2 square into 4 square into 6 square etc. n minus 2 the whole square.